we discuss another work by Robert Tarjan. It's called Applications of Path Compression on Balanced Trees. Basically, what we discuss is another data structure, which is worked something like we discussed, like the union find state structure we discussed in previous lecture. It's usually called union find, but in this paper he called it something Eval-Link-Update data structure. So it's called like this in this paper, but sometimes it is called. So I read it in some another papers. Some context. It's called just Link-Eval. Change title. Oh, we have. Sorry, might have title from. Let's change the title. Good point. Let's go. So what is this data structure? Data structure works like this. Like in previous lecture, we have some forest of trees. We have some something like that. So we have some forests. Let's have 3 trees. Some forest of some trees. Trees are ordered, so we have something like that. Usually we have, doesn't matter. So we have some directed forest. So each tree have a root. So these are roots. Yeah, and each element belongs to exactly one tree. Good. And now we have operations. Each node also contains some value. So in each node there is some value. This value is called the label in this paper, so I will also call it label. So each node contains some label. Nice. Now, what we want to do, we want to be able to perform 3 operations. Basically, we want to complete eval, link, and update operations. We need 3 operations. Let's go. So, what operations do we need? First operation is link. So, link is basically in which direction they do it in. I just want to do it in the same direction as in this article. Makes the parent of the order. So this operation just makes vertex V the parent of vertex W. So we have some tree with a root of V and another tree with a root of W. And this operation basically just makes this V the parent of W. Something like that. So this is basically link operation. It works something like we did in the previous lecture when we make union operation. Yeah, like when we make union of 2 trees, we link one tree to another tree. But here we cannot change the order, so we always want. So we cannot swap these arguments. We always want this W be the sum of this V. Now, eval operation. In eval operation, we want to calculate some sum on a path from vertex V. Let's look on the path from vertex V to the root of the tree. So this vertex V, and then some. So this is the root of this tree. We want to take this path and calculate some function in this path. Let's say we have, let's enumerate them. So let's call them something like A0, A1, A2, and so on. This is the K. So we want to calculate something like A0, something A1, something A2, something and so on, something AK. So this is some abstract operation. So this is some binary operation. What properties we have from this operation? By now, the only property you want from this operation is to be associative. So this is some very different word. Difficult. Associative, right? This is some associative operation. Associative means you can change the order of executing this operation. So if you have some x, something y, something z, you can calculate it like this, or you can calculate it like that. So the result will be the same. That's quite common property for different operation. For example, you have for sum operation, for minimum, maximum, some other operations I know, greatest common divisor, and so on. If you watched the lesson about segment tree already, we had about something like that. We have some abstract operation, and we needed to be associative to be able to perform these operations. That's all. And final operations update. And update will just modify the label of the vertex R. So vertex R must be the root. And this operation makes the following. It just updates the label of the vertex R. Like this. It just applies this operation with this argument to this label. You can watch the previous lecture on YouTube. The link is just below in the description of this channel. That's all. That's all. Okay, is it clear by now what we want to do? We want to make the following data structure. We want some elements be organized as some trees. Each element belongs to exactly one tree. And we want to perform these three operations. First operation will combine two trees into one big tree. So we take this vertex and just link it to this vertex. So they became one big tree. Second is eval operation. We just calculate the sum on this path. Sum using this binary operation. So we have some binary operation, and we use this binary operation to calculate sum on this path. Sum of labels, yeah. So we have labels in each vertex, and we calculate sum of these labels. Nice. And finally, update just updates the label of the root node. So we take the root of the tree, and we may update the label in the root. Is it clear by now? Okay. This should be quite simple by now. Let's go. Now what we'll do, we will try to basically it's in the next semester we'll talk about link-cut trees, and obviously you can do all these operations using link-cut trees. In link-cut trees you can do all these operations in log n time. If you're not if you don't know what is link-cut tree, we'll discuss it in the next semester. It will be fine. But just here we will try to do it faster than in log n time. So we'll try to make these operations actually faster than in log n time. And the reason we will do it is because we don't have cuts. In link-cut trees, you can link two trees and you can cut tree. So you can like merge two trees into one, and you can like split tree into two separate trees. Here we only need to link these trees. So we'll be able to do it faster than in log n time. That's good. Go. Now, first observation. How can we first we will try to apply the path compression. It is the same technique we discussed in the previous lecture. This path compression. How to apply path compression to make these functions? Pretty simple. So when we call eval function, so you call eval of some v. So you have this vertex v, and you have some. So this is r. Yeah, it's pretty hard to Google it. Yeah, that's true. You may Google the article, the main paper, so it's application path compressions. Maybe it's easy to Google it as Eval-Link-Update. I didn't try it, but you might try it. It's not very popular data structure. That's why we have this lecture in bonus, because who else will tell you about these data structures if not me? Okay, so we call eval operation from this node v. So when we call eval operation, we follow this path and calculate the function like we did in union find, and then we will make link. We will make this v the sum of this vertex r. So after we find this sum, we will connect this v directly to this vertex r, and we basically connect all vertices on this path to this vertex r. How we'll do it? We will do it by modifying the labels. So now they have labels, let's say A0, A1, A2, A3. Here we have A4. So after we apply path compression, we'll have something like this. We have vertex R with label A4, and we have this. This is vertex V, and these are 1, 2, 3. And we'll change labels in such a way that this sum will stay the same. For example, for this vertex, sum must be A3 plus A4. So we just leave A3 here. For this vertex, sum must be A2 plus A3 plus A4. So we make it A2 plus A3. So now when we try to calculate sum for this node, here it is sum of these three, and here it is again sum of these three. So the result for this node will stay the same. And here we'll make A1, A2, A3, and for this vertex it will be A0, A1, A2, A3. That's all. So what you do when you do path compression? You follow this path. Calculate the result, and then connect all these nodes on this path directly to vertex R, and modify the labels in such a way that the sum is the same as before. Is it clear how to calculate this sum in linear time? It's quite easy. You just calculate this sum from right to left. So first you calculate this, then you calculate this by A2 plus this, then this will be A1 plus this will be A0 plus this, and so on. So you just calculate them from right to left, and in linear time you can calculate all these results and connect them directly to R. No, update operation is very easy. When you make update operation, you just update the value in the root. It's by now it's very easy. we update only the roots. We update value only in the root. We never update, so we cannot update this vertex. If we could update middle nodes, then it will be difficult. But we update only the root node. And root is the same. We will never change this root. So after we apply this path compression, the root is the same, so we can change this root. If we change the root, we will change all the values in the same way, and so on. Okay, that's the first part. We can apply path compression. Now let's remember the previous lecture. If we apply path compression, when we calculate something like that, then what will be the time complexity? Well, the time complexity will be, if this tree is not balanced, then time complexity will be something like that. We proved this in the previous lecture. Well, it's about log n, but not exactly. It's log n when you have small m. If you have big M, this is constant. If m is between n and n squared, it's something in between. If tree is balanced, tree then time complexity will be big O of alpha m. Yeah. So these two we just proved on the previous lecture, right? If you didn't get the proof, it's not that important. Let's just you can just believe in this lecture, then these time complexities are correct. The proof was kind of complicated. We will not use that proof. We will just say that this proof is correct. Okay. So in this lecture, we will just believe that if a tree is not balanced, we have this time complexity. If tree is balanced, we have this time complexity. Okay. So in this data structure, no one promise us that the tree will be balanced, right? So if you make some arbitrary links, the tree will maybe not balanced in the end, right? So if you just make these links, you may end up with some non-balanced trees in the end. So if you just apply path compression to these to these operations, you will have this time complexity. That's already not bad, right? So this time complexity is still about log n. So if you just need some fast data structure, something about log n time, you can just make these operations very simple. Again, how to make link operation? When you make link operation, you just make this v parent of v. So here you just make parent of w equal to v. Here you just update this label in this way. And when you call eval, you just follow this path, make path compression. That's all, like 10 lines of code. Very simple. So if you just want some pretty fast data structure, you may just implement very simple operations, apply path compression, and you have this time complexity. But if everything was that simple, we'll not have this lecture. What we want to do is to have this time complexity. Okay. Unfortunately, it's not always possible. We will be able to achieve this time complexity for some specific operations. So for some operations, we will have this time complexity, and also for some special cases. Okay. So let's go. Can I erase something? Is everything clear by now? You just write something in the chat each 30 seconds, okay? Just to keep me notified that you are all right, okay? By now everything must be pretty simple, right? So we just have very simple operations, apply path compression. Path compression is simple, so it's all quite simple, man. Let's try to achieve this time complexity. Okay, go. Just write this. The first special case when we can easily achieve this time complexity is when you have some special operation which have some inverse values for each value. So if you have if for each x there exists some x minus 1 such that if you have x and connected to x minus 1 will be equal to 0, and 0 is some value. 0 is some value that for each x, if you apply 0 to x, you will have x. This is 0. How this is useful? I'll discuss some algorithms when you can use this. Or maybe I will not discuss them today. So there are a lot of different applications of this algorithm in some strange of this data structure in some strange algorithms. Like you can use it when you build the minimal spanning tree, when you build dominators tree, in some maximal flows algorithm. I don't know. Do they show some other applications? I know there should be some other applications. So in some algorithms you have some trees and you want to calculate some functions on these trees. So we'll discuss such algorithms in the next semesters. Maybe in the next, some we'll discuss in the third semester, some in the fourth semester. So at some point we will use data structures like this. What I was talking about? Yeah. So you have some operation, and for each element there is an inverse value. So for each element you have inverse element, so that this sum equal to 0. Simplest case is, for example, if you have some if, for example, if the operation is plus, then x minus 1 is simply equal to minus x. So, by definition. So if you have numbers and you want to calculate sum on a path, yeah. So when you want to calculate sum on a path, you want then the inverse value is just minus x. So you have x plus minus x equal to 0. Cool. Let's do. So how we will achieve this time complexity? We will achieve this time complexity by building balanced trees. So we have our tree. So we have this real tree. This tree may be not balanced. Okay. Let's have some vertices. Like this. It is not balanced. We will build another tree, what's called virtual tree. This virtual tree will have all the same nodes as a real tree. We'll have the same. Let's see here. Let's have some more. something like this. It will, these three will be balanced. So these three will be balanced, and all evals will give the same results. So we only compare in the balances tree works. No, we can apply path compression to any tree. Path compression is a very simple method. You can apply it to any tree. It does not require the tree to be balanced. But if tree is not balanced, then you will have this time complexity. And if the tree is balanced, we will have this time complexity. So if we just apply path compression to this tree, we will have something like that. And if we apply path compression to this tree, we will have this time complexity. And that's what we need. Let's go. Now, for example, let's build it for this tree. If you have, for example, if the operation is sum, so if this operation is plus, and you have some numbers here, let's see, like 1, 3, 5, 4, 2. Let's put some labels here. So here will be 5. For this vertex, it should be 3. For this vertex, the sum should be 1 plus 3 plus 5. It's 4. And here it should be 7. And here should be 2. So if you look on how eval operation is calculated, then in this tree, all results are the same as in this tree. So we can use this tree instead of this tree, and we will do it in such a way that this tree will be balanced. That's the plan. So we'll kind of make some how to call it? Something like equal tree. So we have our tree, and we will have some another tree, which is in some case equal to our tree. In case of this operation, so this operation will give the same result. But this tree will be built to be balanced. And when this tree will be balanced, we will apply path compression to this tree and we'll achieve the good time complexity. Yeah, at some point we will touch the root actually. In some cases, we will try not to touch the root, but actually in this case, we will touch the root. Now, let's go. So, if we have operation like this, so we have some inverse element for each element. How can we build the tree balanced? We will build in very simple way. So imagine you have some operation Link-VW. So you have this vertex V, you have some tree here, this vertex W, you have some tree T, and you want to link this W to this V. Let's see how the eval operation will change for all nodes of this tree. So what will happen to the results of eval operation? So for this tree, a result of eval operation is the same as before. So here, if you look on any vertex here, after we make this link, this result is the same. So here is the same. And for each vertex here, it's too long. Let's say like that. Let's say E of x equal to previous E of x. So if you have some vertex x here, so this is the previous result of eval. This is the next result of eval. Yeah. So the next result of eval is the same as before. If you have some vertex here, say y, and you calculate eval from this vertex y. Then, before you make this link, you calculate sum on this path, yeah? And when you make this link, you calculate sum on this path. So this new value of eval of y will be the old value plus v. No, label of v. I'll just put it. Okay. You take label of vertex v and apply this operation. Yeah. So we'll get new result in this vertex. Makes sense. Now, let's remember how we made the tree balanced when we make union find data structure. When we make union data structure, union find in previous lecture, yeah, we try to build the tree balanced by connecting small tree to big tree. Yeah. So when we connect some small tree to big tree like this, then instead of this, we try to do this. We try to make small tree and connect it to big tree. This is how we managed to build the balanced tree in the previous lecture. We will try to do the same. So in this case, if this tree is small and this tree is big, so if size of v is less than size of w, then we will try to connect this v to w. So we'll try to reverse this edge. So if we make this v son of this w, then you have the different results, right? So this eval function will not stay the same, because now in this tree, eval function gives the same result, and in this tree, the eval function will include this vertex w. So we need to fix this. How we will fix this? Very simple. Let's see. So let's start from this tree w. Yeah, we'll say this. Yeah, well, it's exactly like that. So in this tree w, we want the next, the new value of this eval operation be the old result plus vertex v. So I will take this vertex v and just apply it to vertex w. So this label of vertex w will be old label of vertex w plus this vertex v. So here I apply this vertex v. Now for this tree, the result of eval operation for each node will be like this. So here, if you take any node in this tree, then new result of operation eval will be the old result plus v. So it is the same as here. Now let's look on this tree. In this tree, if we take any vertex x, what is the result now? Now result is we go to here, we apply v, then go to here, apply v, and then apply w, and then apply v. And we want it to be the same. So to fix this, we will simply apply the inverse operations of this. So we go to v, then to here, and we want to have an inverse of this. So here we will apply, we need to do it in correct order. So we apply w, then v. So to reverse this, we need to apply v minus 1 and then w minus 1, right? Looks fine. So will be old label of v, then apply v minus 1, then apply w minus 1. Yeah, makes sense. So when we follow this path, we get this sum plus this element, and we want to like neglect this element. So we make this change to this node to neglect this change of this node. So this node contains value this. Yeah, it's not this labels this. So let's change. Here I have label. Here I have v. Yeah, let's have labels everywhere. Like this. Just too many text in this whiteboard. My whiteboard is small, so I'll usually skip this L. Just say that I apply vertex V, because it's kind of what you do when you apply this operation to labels. So when I print something like this, I mean the label of the vertex. Okay. It's just for simplicity, because my board is small. Makes sense. So new label of yes, I apply LB to L minus. Yes. You can make 0 here, so it will adjust label of W minus 1. Makes sense. Okay. Let's have some examples. So, for example, you have some tree. You have like vertex with label 3 in the root here, and here you have vertex 2, and in another tree you have vertex, let's say 4, and here we have 5 and 1. So you have something like this. You want to connect this, and this tree is big and this tree is small. So you want to change the direction of this edge. So you put this here, this tree, and now you apply this operation. So a new label of W will be sum of these two labels, so it will be 7, and new label of this will be minus 4. So again, in this tree, the results of all operations is the same. If you take some if you take this node here, the sum is 5. If you take the same node here, the sum of this path is also 5. So tree is different, but the result of operation is the same. That's all. And now, if we always connect small tree to big tree, the final tree will be balanced. Again, like we discussed in previous lecture. And when we apply a path compression to balanced tree, we will have the inverse Ackermann time complexity. Cool. Oh, I lost half of my viewers. Oh, no, that's fine. That's not very popular topic. Okay. Fine. Go next. Let's go next. Again, you're too quiet again. Just say something. Now, that's the first special case when you can achieve the inverse Ackermann time complexity, when this function is such that you have inverse element for each one. But that's not very usual case. There are a lot of different binary operations which don't have the inverse operation. For example, one of the most popular operation is minimum or maximum. Can I erase this? If we do update on this, what? How to make updates? Yeah, we changed the root of the tree. But yes, okay. How to make updates? You find this node R, which was so in the real tree. This vertex R was the root of the tree. In your virtual tree, this node R may be not the root of the tree, so it may be somewhere here. Yeah, the roots changed. What you can do, what you want to do when you apply update operation to the root, you will change the result of operation to all tree. So after you make update, the new result of operation will be the old result. We have x for each vertex v will be the old result plus x. So if we want to make update, we may find the root of this tree. So we take this vertex instead. R2. We take this vertex and apply update to this root. It will give you the same result. So if you just take this root and apply this operation to the root, the result will be the same. So if you take any vertex v here and here, for this vertex v, result will be changed by this x, and for this vertex v, result will be changed by this x. So result will be the same. So when you need to update some value in the root, you take this vertex r, find the root of this tree again by path compression. Find this actual root, this virtual root here, root of in this virtual tree, and apply this update to this root element, and it will give you the same result as applying this x to this. Okay. Yes, good. That was a good question. That was a good question. Yes, we don't need to maintain the real tree. Yes, in all these algorithms, we will never need to maintain the real tree. We always will maintain all the virtual tree, and we just make sure that our virtual tree is always the same as the real tree. So we don't need to maintain this real tree usually. We just maintain this virtual tree and maintain the property that the results in this virtual tree is the same as the results in this real tree. Okay. Let's go next. Let's move next. Let's move to the maximum. For maximum, it's a little bit more complicated. So why can we apply the same technique as here? Because we cannot change this to this. When you apply maximum, you have this one in this. So you want to make link. So you have one here and two here. Yeah. So you want to make this link. You cannot. You have some trees here, some big tree here. You cannot just reverse this edge, because you want a result for this vertex be equal to 2, and the result for this vertex be equal to 2. So if you just change the direction of this link, so this is x, this is y. Well, it's v double. V and this w. Sorry, it is the first time I have this lecture. This will be W, this will be. So if you just reverse this edge, you want a result for this vertex be equal to 1, and for this vertex result should be equal to 2. And you obviously cannot do it, right? You cannot put some values here and here, so maximum here is 2 and maximum here is 1, because this maximum includes this vertex. So this maximum will be greater than this maximum. So we will apply different technique. Ready? Whew. Let's go. No, let's start with some simple properties. So let's look on some properties of maximum function, which will allow us to make fast algorithm. Let's see. So if you have some node, and the label is x. Let's look on the path from this node to the root. So let's look on this path. Oh no, it's much more complicated. No, in the idempotence is not enough. We need function that we have some total ordering. So maximum is defined when you have some total ordering of all elements in your group. So we will use this. Let's see. So imagine you have this vertex x. Let's look on this path. First observation. If all vertices on this path, so if all these vertices are less than x, less or equal, let's see. Then, what can we do? We can just ignore these vertices when we calculate something inside this subtree. So if you take any vertex here and try to calculate result for this vertex, you can just ignore all these vertices. Because you follow this path, calculate maximum here, then you meet vertex x, and all vertices here will be less than x. So when you calculate maximum, you can go here and then ignore all this. So you only need this part of this path. That's first observation. Second observation, let's have something like this. Opposite. If you have vertex x and not all of them are less than x, so at some point you meet vertex y and y is greater than x. Greater or equal, let's see. And if you move from x to the root, and on this path you meet another vertex which is greater or equal than x. What can we say about this vertex x? Okay, any ideas? Let's stop here for a little. What can we do about this value x? Any ideas? Oh, so you missed the beginning. Okay, no, but we just started the most complicated stuff, so you missed the first part. That's too bad. What we want to do, we want to be able to calculate the maximum on a path from the vertex to the root. That's the current state. We can map all the subtree nodes to y. Yeah, no, we can always apply path compression. I want to change this label actually. What I want to do. Yeah, we can always apply path compression. That is true. We can apply path compression and we make these nodes directly white. The more interesting part is the most interesting part that we don't need this label x anymore. Yes, we can change this x to y actually. So we can change this x to y, and the result will be the same. Again, if you take any vertex in this subtree, you follow this path, this x will never be the maximum in this path, because for each path, this y is greater than x. So this x will never be the maximum on this path. Cool. That's all. That's all we need. Now let's make the algorithm. The algorithm works like this. Again, we have our real tree, and we want to build some virtual tree which have the same the same results of eval function. Now it will be a little bit more complicated. We will transform our tree into some sequence of trees. So we have in real tree, we have some tree with some root r. In our virtual tree, it will be transformed to not one tree, but a series of trees. So we'll have this vertex r and some tree. Here we'll have another tree. It's called r1. So each tree in the real tree will be transformed to a series of trees in the balanced tree, in the virtual tree. Okay. In this tree, these vertices are somewhere, so we have something. R1 is here, R2 is here. So these trees contain the same set as this one tree. So all these three trees contain some vertices from this one tree. Clear enough? Hope clear enough. And now we will maintain the following property. First property. Each of these small trees will be balanced. So all these trees are balanced. And we will connect them in a sorted order. So these labels in the root words will be sorted. So this label will be less or equal than this will be the equal to this. I compare only labels in the root. So I have these three roots. Label in this root is greater than label in this root. Label in this root is greater than label in this root, and so on. Inside these trees, there might be some different vertices. I don't care about inside of these trees. I care about only these roots. We have some example. Let's have some examples. We have some vertex, let's say. Let's think again something like and they have some values, let's say 3, 1, 5, 4, 7. So we can transform them into something like you have vertex A, here we have vertex B, for example, here you may first vertex C, What I want. Let's have like this, for example. Is it the same tree? Not exactly. Okay. So we have this. Let's make this dashed. We have 3, 1. I have the same labels. No, that's boring. You may change the labels, but you care only on the results. Let's just to make it more interesting. Let's add F here. So we can add F here. Let's make it like this. So we will add F here and apply 7 here. Clear enough. Again, we have this tree in our real tree. We transform this into series of trees. So we have 3 trees, 1, 2, and 3 trees. These roots are sorted. So this 3 is less or equal than this 4 is less or equal than this. And this set of trees contains all the elements from this one big tree. So we have the same 6 vertices here. And the result of eval function is the same. So if you take any element, so we have to calculate result of eval from here. So we follow this path. So result will be 7. If you take this calculate result of eval, you follow this path, but result will also be 7. So result of eval should be the same. The set of vertices should be the same. And each of these 3 must be balanced. Okay, I lost another half of my viewers. Anyone still alive? Okay. Just print something in the chat, just to make it look like something interesting is happening. Go. Now, that's the plan. So we will, for each tree, we will make something like that. Yes, I want result for this f be equal to 7. So I need to change this label to 7 to have this result, to have the result of eval function be equal to 7. Yes. Okay. So labels are different, but the result of eval function is the same. Yeah, that's the plan. Well, let's go. So how do you calculate the eval function? So eval function is very simple. So when you calculate the eval function, eval, so you have some vertex v. What you do? You simply calculate the eval function as before, but you calculate the eval function not to the root of the tree, but only to your local root, to the root of your small tree, of this tree. So you follow the path to the root, but only to your local root, so RK, something like that. So you inside of this tree, let's make it like this. So this is the real root, this is your local root. When you calculate eval function from this vertex, you may follow not the whole path to this root, but only path to your local root. Because all these vertices are less than your root. So all these vertices are less or equal than RK. So you don't need them when you calculate eval from this vertex. You may go only up to this vertex and don't go here. So because of this property. That's all. that's how you make the eval function. You just follow the path to your local root. Each this small tree is balanced. So when you apply path compression to this path, you will have inverse Ackermann time complexity. Because you only apply path compression to the balanced trees. Each of these trees balanced. So when you apply path compression inside this tree, you will have inverse Ackermann time complexity. Yeah, simple algorithm. I told you that is simple. Now let's talk about links. We need to talk about links and updates. First, let's talk about updates. Updates. Link will be fun, yes. Not very hard, but kind of fun. Let's first make update. Okay, in this method we will not change the root. So this root will be the same in the virtual tree as in the real tree. So when we make update, we will change the label of this root node. What will happen? So you have something like that, and then you change the label of this root element. The problem will happen that these inequations will be not satisfied anymore. So you have this sequence. Let's have them dashed. Let's have them dashed. So when you apply update to this vertex, so you have some new label will be old label plus maximum and this of R and X. Yeah. Operation is maximum. Yes. Before we apply this operation, we have this property. After we apply this operation, the label will be increased. So when we increase this label, this equation may be not satisfied. So let's calculate the new label of the root, and then find all the children. No, actually, if the root is changed, then it will be equal to x, right? So maximum is equal to r or x. So we either not change the root or we change it to x. So if it's less than x, we will change it to x. That's what happens. So if we just make it equal to x for simplicity. So let's make the label of the root equal to x. Now let's find all the elements which are less or equal. No, doesn't matter than x. Let's find all the elements less or equal than x. Now, what can we do? Again, like we discussed before, if you have some element and above you have some element greater than this element, you can change this label to x. So we'll find all the roots less or equal than x and change them to x. Yes. We can do it, the result of eval function will be the same, right? And now what we'll do, we will merge these two trees into one big tree. So we'll take all these trees and merge them into one big tree. So we will take all these trees, so we have some small trees, and merge them into one big tree. Actually, no, without this. We don't want to touch the root, only these three trees. So we take these three trees and merge them into one big tree. It's something like that. So we take these three trees, merge them into one big tree, and everything else is the same. So that's the final state. That's all. That's how we apply operation update. Again, we update the value in the root, then find all the small roots less than x, change their labels to x. Actually, it's not important. You may not change the labels to x, just for simplicity. Yeah, and then merge these two trees into all these trees into one. And when we merge these trees into one big tree, we apply the same heuristics. We connect small tree to big tree. Yeah, we merge all this small tree to the big tree. So this tree is still balanced. That's the plan. Let's see. That's all quite simple. Again, let's stop here. Let's talk about time complexity. Why did we merge the updated nodes tree into... to make time complexity good. We need to merge these trees because if we don't merge them, each time we apply update operation, we need to find again this node and change these labels again. We want to be amortized time complexity small. So if we make long operation, so we find many roots and change a lot of labels, we want to compensate this time complexity by decreasing the potential. Yeah? And decreasing the potential is just decreasing the number of trees. So if we find k trees, then time is k, but delta phi will be minus k. Well, if phi is the number of nodes, number of trees. K minus 1, something like that. So we find these k trees, spend k time, but to compensate it in the final time complexity, I want to decrease the potential. So I will merge all these trees into one big tree. So total number of trees will be decreased by k minus 1. This will compensate time complexity. Okay. Whew. That's almost all. Now we just need to make links. Almost. Going quite well. Yeah, that's where it's link here. Link. So what's going on when we make link operation? Well, we want to merge these two trees. So we have this vertex v. We make w son of v, right? So we have this vertex v. Let's may use different colors for v and w just to make it more visual. Let's have this vertex v, and it contains some number of trees, right? So we have this set of trees, and we have another set of trees for vertex w. So we have this vertex w. Yeah, and I kind of want to do this. I want to connect this w to this v, make this v parent of this w. Updates are constant time amortized. Yeah. Updates have amortized constant time. That's right. All time complexity is inside will be held inside evals actually. Yeah. No, again, like in union find data structure, when you make union, you have constant time complexity. Well, here we have update. It's kind of the same. You make update, you have constant time complexity. Yeah. Can be merged almost once in the expression. Yes, each node is merged exactly once. So if this node is merged to another node, it became its son and it's forever, like in link-cut or like in Link-Eval, or in union find, like in union find. When you merge two trees, they are merged forever. Yeah. And then you apply path compression. Yeah. Then here you have one big tree. This tree is balanced, and you will apply path compression inside this tree. Okay. So now links. You want to be able to link this W to this V. That's kind of tricky, because you have a lot of trees here, a lot of trees here. You cannot just link them. So what you will do, you will merge something to something. Let's see. Let's look on the total size of all nodes here. So let's look on total number of nodes here and on total number of nodes here. Total number in all these small trees. So let's look on all nodes in this set of trees and all nodes in this set of trees. And look which is smaller. So let's look where we have the smallest number of nodes. There are two possible cases. This tree is small. This set of trees is smaller than this set of trees, or this set of trees is smaller than this set of trees. Let's try to solve both of them. So, for example, if size of W is less than size of V, size of W is the total size of all these nodes. So we'll keep track on total size of this node. So this size is size of W. So it's total number of nodes in all these trees, not only in this small tree, but in all these trees. Okay, and the same here, and the same here. So size of V is the total size of all these small trees. So if this total size is less than this total size, then we will do the following. We will take all nodes here and connect them directly to V. So we'll take node V, so here we have the same drink. These are the same. Now we'll take all these nodes and connect them directly to V. One of them is W. Like this. Now, later we'll prove that it will give us the good time complexity. Okay? Now, what happens if the opposite, if this size is greater than this size? So if size of W is greater than the size of V, then we will do kind of the opposite. We will take all small trees here and connect them to V. So again, we take this V. Let's make it blue. We take this V, take all the nodes in this set of nodes and connect them to this V. So we have three. Yes. And then take this whole chain and connect this chain directly to V. Something like that. Here we have W and through here. this is W. That's all. That's the whole plan. Again, let's see what's going on. So you want to connect this W to this V. And you want the result of this, how do you call it? A result of this of eval function be the same. So if you call eval function from some node from here, so you need to follow this path to vertex W and then to vertex V. Here you will do the same. You go to the vertex, to your local root, you don't need this W, and then to vertex V. So this vertex V will be added to all paths for all vertices in this set. And for each vertex here, the path will be the same. So for all vertices here, the path is the same. For all vertices here, we'll add vertex V. The same here, for all vertices in this set, we will add vertex V to this path. For all vertices here, yes, I almost forgot. At some point, when you do this, you may again break this property. So you need to make the same procedures here. So yeah. Yes, you also need to find all the nodes here which are less than V and apply the same operations here. Yeah. Okay. Again, for all vertices here, if you take the path from vertex to the root, this V will be added to this path. And for all vertices here, the path will be the same. So you follow the path to your local root and so on. Each node can be root almost one. Yes, in this big tree, yes, the tree is also changed almost one. Yeah. So if one vertex is not a root anymore, so when you merge these two trees, this W is not a root anymore. So it will stay not root until the end of the algorithm. So if some vertex is not stops being a root, then it is not a root until the end of the algorithm. Yeah. So the life of each vertex is like this. So at some point, this vertex was the root of the tree. So let's see some vertex V. So it starts as a root of the tree. Now at some point, we merge it to something. So this vertex is not a root, but it is local root. And then at some point, we make this merge. So this vertex V is not a local root. So it is inside something. So this is the typical life of a node in this data structure. It starts as a root, then at some point we merge it, so it becomes some local root, and then we merge this tree to some another tree, and it becomes just some internal vertex. This could happen during the link operation. Yes, when you merge these trees, and when you do this, yes, when you do this, you make all these nodes not local roots. So now they are not local roots. So this is one single balanced tree. So here we have just one single balanced tree, and here we have one single balanced tree. So when you make link operation, these vertices are not local roots anymore, and here also. That's almost all. Now we just prove that this tree is balanced. That's all. That's the plan. The amortized time of link is also, yes, the amortized time of link is also constant. Because when we travel along some path, we also decrease the number of trees. Yes, correct. Yes, the amortized time of link is also constant. Yeah, final part. What we forgot to prove? We forgot to prove that the final trees are balanced. How to prove that the trees are balanced? Quite simple. Well, look, how do we construct these trees? Let's look on here. So when we apply update operation, or the same when we make the link and combine these trees. So when we apply something like that, we take the number of small trees in this chain and merge them into one using weight heuristics. So we connect small tree to big tree. Let's look on these edges. Let's call them good edges. I need more colors. I'm not sure if it's green is visible. Let's call these edges good edges. Visible? No, quite enough. So let's say these edges are good edges. You can't read this. What is good? Good edge has a very simple property. If you have a good edge from X to Y, so if this edge is good, then the size of Y is at least twice more than the size of X. Now, let's prove that when we apply this operation, all these edges are good. No, that's quite obvious, because when we make this operation, we connect small tree to big tree. So every time we connect small tree to big tree, the total size of this tree is at least twice bigger than the size of this small tree. So when we connect all these edges will be good. Yeah. But that's simple, right? Now let's talk about other edges. Not all edges in this data structure are good. For example, when you make something like that, so when you make this link and you want to connect all the trees from this set of trees to the vertex V, it may happen then this vertex V actually connects some small trees. So you have some. So when you do something like that, you may have some vertex V, which have some small tree, but you have big trees here. So these trees are big, and this tree is very small. And when you apply this W, so the total size of nodes here is big. So you have this W, you have one big tree. Again, the total size of W is less than total size of V, so we make this procedure. But the size of this small tree is greater than the size of this small tree. So we may connect this big tree. So this small tree of W may be bigger than this tree of V. So it may happen. So in this case, we will connect big tree to small tree. Sometimes we do it. Did I lost all my actually the number of viewers is actually increased. That's strange. I forgot the word. Mediocre. I remember right. That's difficult word for me. I know how to pronounce it. It's like mediocre, right? I will check my paper. Sorry. Mediocre means I'm not good, not quite good, but good enough. Something like that. So we will say that we have mediocre edge if we have the following property. If we have two mediocre edges one by one, so if we have x, then y, then z, and we have these two mediocre edges. Then if we have two mediocre edges y by one, then size of z is at least twice size of x. And I claim that all edges here are mediocre edges. So if you look on these edges, they all are mediocre edges. So all edges here are mediocre, all edges here are also mediocre edges. So basically, all edges we create on these operations are almost good. So if you apply two edges like this, you will increase the size of the tree at least twice. Well, let's prove this. It's actually not that hard. So what happens if you have a situation like this? If you have a situation like this, it means how can it happen? Let's raise something. Let's raise this. So, how can you have two mediocre edges one to each other, next to each other? It's something like that. So, you had vertex x. Then at some point you merge something to something. So this x became the sum of this y. Okay. So you have this vertex x. Then at some point you merge this x to some vertex y. It means that you have, so this vertex x, let's look on both of them. It doesn't matter which part do you like. Let's use this. So in this, so you have so you have something like y and something. Then you have something, and here you have x. And then you apply this operation. You apply this operation if size of w is less than size v. So if you apply this, you will have x the sum of y, right? No, as well as all these other vertices. So all these other vertices will be also the same. We just apply this operation. And here size of x, size of y is greater than size of x. But this size is different size. This is like subsize. This is size of the small tree. Yeah, and this is the size of the whole element. These different sizes. Okay, this is called subsize in this paper. Let's go. So size is the total size of all elements in the whole set, and subsize is size of this small tree. So when we apply this x, when we link these two sets, the x became the sum of y. Now, this y should become the sum of z. How can it be? No, because at some point we link this set to something which contains vertex z. So we have z and something. And we have this, we have y, x, something, 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 something. And we link them. I want this y, this x, and this. I want them. Sorry. I need this dashed edges, right? These edges are dashed. It's a little bit too complicated. Oh, like this. So, okay, here we have some trees, and here we have some trees. And then you apply link operation, so you link these two trees. So this x became the son of y, because you apply this operation. Yeah, well, like this x is one of these trees. So x became the son of y. So here x is the son of y. We have some trees. Now you have this y. It may be some of another something. And then again you link this to this, and you apply operation like this. So this, all these trees became the sum of this z. So you have z, then here you have y, and here you have your x. Here we have some. And all these vertices also became the sum of this z, because when you make this link, you take all these trees in this chain and connect them all directly to V. So you take all these nodes here and connect them to vertex V. So you have this here, you have all nodes. Now let's look here. So here we apply this operation because size of y is greater than size of x. So this size is greater than size of x. Just remove it here. But it doesn't matter. Size of z should be greater than size of y, but it doesn't matter. We take this. Now let's look on all these small trees. When we make this operation, all these small trees are now here. So here are all these small trees. So total size of all these small trees are greater than size of x. And now when we apply the second link operation and make this y the child of z, we take all these, so we take this. We take all these trees and make them separate sons of this z. So we connect them. When we connect this y to z, we also connect all these trees to z. So now these trees became here. And now when we calculate the subsize of z, we include all these nodes. So here the subsize of z is at least twice bigger than subsize of x. No subsize here. Well, for x is not better, but because x is not. Subsize is the size of small tree, and size is the size of the whole set, right? That's a little bit difficult, but that's all. And now here, for vertex z, all these nodes are children in this small tree. So here we have this small tree. This small tree includes all these trees from here. So after second link operation, these trees will be merged into one big tree. So for this vertex Z, total size of this small tree is at least twice bigger than size of this X. That's all. That's why if you take two mediocre edges one by one, then the size will be increased at least twice. Because if you make two link operations, you will link all these into one big tree. Well, the same thing here. Here, if you apply this operation, it means that the size of this W is greater than size of this V. And when you apply the second link operation, you will merge all these small trees into one. So again, you can do it by yourself. It's just the same. That's all. And so finally, simple observation. If all edges in your tree are either good or mediocre, then your tree is balanced. If for good edges it's obvious, yeah. If you have good edges, then you have balanced trees, right? Because each time the size is increased twice, yeah. For mediocre, it's kind of the same, but the constant is not 2, but square root of 2. So let's prove the following. So number of nodes with rank k is at most n divided by square root of 2 power k minus 1. Yeah. Something like that. Okay. And finally, let's focus. This property is a little bit different from we had last time. Last time we proved that the time complexity will be inverse Ackermann if we have properties something like that, more than n2 power k. But it actually doesn't matter. You may have the same proof, but you have different constant. So this constant here only affect the constant factor of your time complexity, not the asymptotics. So we'll just use the same proof as we did on the previous lecture for this bound on the number of nodes and have the same time complexity. It's also be inverse Ackermann time complexity in the end. That's basically all. Thank you for watching again. I'm not sure if I want to have another lecture till the February, but if I will notify you in the Code Forces blog. I hope it was helpful. I'm not sure why you're watching this. I like this because it's kind of little more complicated stuff. So when you learn something about algorithms, then first you think that algorithms are simple. So you have some simple algorithms, like you have, I don't know, Dijkstra. You have some simple data structures like queues, stuff like this. And you at some point you kind of think that all algorithms are pretty simple. And I know. I like when something is a little bit more challenging. So some algorithms are a little bit more challenging than just regular algorithms you used on the program. You will never. I believe you will never use these algorithms in the code. But no, actually, for this algorithm, I think it's possible to use in the code. This, yeah, I think it works actually pretty fast. all operations are simple and complexity is good, so I believe it has good time complexity and good constant factor. So you maybe have chance to use it at some point, but I'm not sure. Usually you have much simple algorithms in your in the contests, not because during the contest you have such limited time. Okay, so thank you for watching again. See you in February, I think. That's all. If you have any ideas about future lectures, just let me know. Okay, bye, see you.